Now camera is on. Thank you for reminding me that is very easy to forget. So, now, where were we yesterday? We did have a look at. We were discussing carbon dioxide and in various forms. Calcium carbonate, for example, it's a quite distant form of carbon dioxide, but it is at least half of it. The carbonate ion is a close relative to carbon dioxide. Solubility in general of minerals, carbonate minerals, or even other type of minerals that form react with carbon dioxide. One can say it is worth to discuss them in a situation like this. From the solubility of calcium carbonate, one can draw some conclusions, assuming that calcium carbonate is just dissociating. And if we know the value of the equilibrium constant, the solubility product, sometimes it's called only Ks for the equilibrium constant for solubilization reaction or solubility reaction. But if it says S or SP, it's probably the same. Even without any extra characters, if there is a K in a closely associated with a reaction like this, it should be interpreted as the K, the equilibrium constant for this very reaction. If we use the some accepted value, here I used 3.36 times 10 to the minus 9. And if you look it up on the internet or in some table, you may very well see other solubility products, 3.5 or 5 times 10 to the minus 9, I think, and that is the value in book of data. Well-known table used at Stockholm University for the basic courses. But that is not very important. I mean, if you should have a very, very accurate calculation, determination, then you need to take care also of other effects. For example, that this is a base and other things happen. So don't be stressed, just well, take a note of what value you use for the equilibrium constant and then continue with that. Of course, it shouldn't differ several orders of magnitude. At least not, it shouldn't be 5 times 10 to the minus 1 or something like that. Then it's probably some printing error or something like that. From the concentration of carbonate ions, one can that is produced by dissolution of calcium carbonate, one could construct a similar logarithmic concentration diagram for that very concentration. The X value, what was it? Let's see, 5.8 times 10 to the minus 5, and taking the 10 logarithm of that is something like 4.2 or 4.3 maybe, or minus 4.2, minus 4.3 it should be, since it is smaller than 1. And this is exactly where the total concentration line is positioned, at something like, if it would be logarithm here, it would be minus 4.2, but this is minus 10 logarithm because of the p operator here. But this is just a technicality. Medusa, for example, writes logarithm of concentration, and in some sense that is perhaps easier to follow. Calcium carbonate, carbon, I mean, it is related to carbon dioxide, and let us have a look at what happens with carbon dioxide in equilibrium with water. In an open system, that is a system that is in principle where carbon dioxide from the surrounding can enter or leave. Suppose you have a beaker with the system, some solution with the system, then one can say that carbon dioxide from the surrounding could very well enter the system. And of course, the equilibria associated with dissociation of carbon dioxide, or as we say, carbonic acid, when it is dissolved in water. Think of your, what do you say when you carbonate drinking water? In Swedish, we say kolsyrat, carbon acidified, direct translation. So we say more or less that the drinking water is carbonated, which means that it is not carbon dioxide, but it is containing carbonic acid. Now the carbonic acid is mainly carbon dioxide that is only dissolved in water, but that is still not affecting the language that we use for speaking about carbonated water. This is the same as previous, and producing, for example, hydrogen carbonate ions. The hydrogen carbonate can further undergo some proteolysis to form carbonate, or if you start with carbonate, one could go backwards in both reactions. So equilibrium constants, it's for each of the reactions, they are right-hand side divided by left-hand side, as usual. If there would be some kind of water here in a formula, say that there is a, if we don't use H+, but oxonium ions, H3O+, then we should perhaps have a water molecule here. On the other hand, one can say that the water molecule, they are implicitly present since we have aqueous aggregation state here. They are present in the surroundings to the carbonic acid. But without the oxonium, just using this nomenclature, there is no need for an explicit hydrogen or water molecule here in the left-hand side. Acidity constants should, of course, be independent of how you write them. There could be some problems if you literally interpret the concentration brackets here as real concentrations. They should be interpreted as activities, and only the value of the concentration should be used. But still, this is a very, very common way of writing up equilibrium constants. And this is very well. And from this, one can construct diagrams like that. But what about if we take a focus on the open system point of view? If it's acidus, then it's only perhaps the hydrogen carbonic acid that will form, and if it's less acidus, then the hydrogen carbonate will form, because perhaps then the environment will consume H plus, and if it's very basic, then more H plus will be consumed and carbonate will form. This could actually be visualized graphically. This is difficult, I guess, to follow my discussions among the equilibrium constants like that. But I suppose, unless there is some printing errors here, that I exchange plus and minus for multiplication signs, but I don't think I have done that, not here. So the just taking the logarithm of the whole expression for the equilibrium constant produce an equation like that, and the same for the second one produce an equation like that. And then you can reformulate, for example, the here is what's it called, the hydrogen carbonate, so you can express that as a straight line, in fact, in terms of pH, and the carbonate can also be expressed as a straight line. What is this, you wonder? Well, let me show the graph on the next slide. Here is the same logarithmic diagram as we saw before, but with the constant pressure of carbon dioxide and thus carbonic acid. The carbonic acid is 10 to the minus 4.87 from the process that produced carbonic acid from carbon dioxide in the atmosphere. This is a graph showing the solubility of carbon dioxide as a function of pH. So between, say, 0 and something like 6.4, there is more or less constant solubility of carbon dioxide. This is also visible in the previous diagram. Well, here we had another total concentration, but the level of carbon dioxide is, or carbonic acid, is constant until we approach the pKa, first pKa. If we just let that line be straight, so one can say that carbon dioxide is in principle soluble in water, but at pKa the hydrogen carbonate starts to form. So at pH values above pK1, the carbon dioxide will transform to hydrogen carbonate, and the hydrogen carbonate can actually form quite high levels of concentration. So here, for example, at 8.3 or something like that, we have a we see that it's something like PC is free. So we should estimate that if there is an infinite supply of carbon dioxide from the surroundings, then the concentration of hydrogen carbonate in a lake water should be something like 10 to the minus 3 or even higher. What pH do we need for finding the concentration 10 to the minus 2? This is something like 9, a little bit above pH 9. And 10 to the minus 2, that is 0.01 moles per cubic decimeter, which is not extremely much, but neither it is negligible. it will affect a lot of things in sea or lake water like that. Then, in principle, I don't know what is the highest pH in any lake on Earth. Maybe up to about 9 at least, but at pH 10, I don't know. There are some strange lakes, like the Death Sea, for example, between Israel and Jordania. But it's below the level of the oceans. So water is flowing there and then evaporates. So the concentration is, both it is very, very salty. That is perhaps a reason why it is called the Death Sea. And it's also high density, so it's easy to swim there. But I suppose also there will be very, very high pH. It would be very interesting to do an excursion to Death Sea and make a titration of that water. Should be possible. People reading water chemistry close to them, they are probably doing that. So, in principle, you can raising the pH, you can absorb a lot of carbon dioxide. So making 100 moles per cubic decimeter, which is impossible from a theoretical point, from a practical point of view. But here in the diagram, I can of course find extend. I think pH 9 approximately is a practical limit for real lakes and realistic lakes on Earth.
Could you go back to the previous slide and just explain how do we do this reformulation of the equations?
Yeah,
how do you justify it, so to say?
Yeah. It's. I hope it is correct, but now let's see. If we have the equilibrium constant, then taking the logarithm on one side is the logarithm of the other side. Here is a product of H plus concentration and hydrogen carbonate, so that will be plus here.
Okay, it's just a logarithm.
So
to say.
And here is it quote, so that's the minus here. So then I just, what do? I take this one and isolate it on one side. So the pHCO3 I use as a constant value of 4.87. This is just a constant, and pKa1 is a constant. So this will be, and the sum of these two constants are 11.22. So this is the simplified this is the straight line formula for the pH CO3, and similarly here then taking that formula, pH plus PCO3, it's the product here, and then minus. So isolating PCO3 to minus is using that one, but then I use that value here. So we get this simplified straight line equation. That is the reason why the blue line has a slope of 2, while the green one has a slope of 1. Or -1 and -2 actually, but that is related to the fact that the positive y-axis is pointing downwards in p space. This is horrendous in my opinion, but it is actually standard.
So this you could essentially do this for any equilibrium equation.
Yeah.
But in the example you had here, you had to assume that the concentration of carbon dioxide was constant.
Exactly. Yeah.
Right. And if it wasn't, it would have to be a lot more complicated, basically.
Yeah. I mean, then it would. This diagram is a bit non-realistic in the sense that carbon dioxide levels, they are not. They can't be maintained at this level at high pH. Then it's more. This is a better representation of a real system, that carbon dioxide has a constant level up to first pKa, and then it decreases. But suppose bending up this sloping red line will equally well bend up all the other lines. And so this is just a way I try to illustrate that at a certain pH, assuming that we have, we can say that we have a constant inflow of carbon dioxide from the surroundings. Since it is an open system, a lake, for example, has a possibility to dissolve carbon dioxide from the atmosphere. And depending on the pH of that lake, either it will dissolve it only as carbon dioxide, or it will transform it to hydrogen carbonate. And then how much hydrogen carbonate will be possible to dissolve in the lake water? Yeah. In very many lakes, it's something like 10 to the minus 3. And this is difficult to explain unless you assume that there is a constant inflow. And how high level would it be if we assume a constant inflow and constant level of carbonic acid? This is a way to sort of try to estimate what kind of hydrogen carbonate levels we will have. But I agree, this is kind of weird diagram, but at least it fits our purposes of trying to estimate how much hydrogen carbonate could be dissolved in. Why is it so much? The constant level here is, I mean, that is perhaps dependent on, say that you start with carbon dioxide and then change pH. Then, of course, nothing happens unless this is a closed system. Nothing happens with the total concentration, the level here. The different species, they change. But it's no addition or removal of carbon dioxide in any form, either as a carbonic acid, hydrogen carbonate, or carbonate ion. But this is an open system. Suppose that you have another. We can rotate this system, so we have a constant level of carbonate ions. So this one is, the blue one would be what's it called, horizontal. Then the green one would slope something like that. I can perhaps draw. No, stop. So if we would have constant level of PCO3, say some lake water that or some water that come from the ground with some kind of level of carbonate ions, and at high pH it's no problem. it certainly would be present with some concentration, quite low concentration. And what happens when that situation finds a more acidic environment? If this is then it will the carbonate ions will transform to hydrogen carbonate. It will find hydrogen ions from the environment. And what happens when environment got extremely acid? By some reason, how the environment will change pH is difficult to judge from this graph. But this graph is only showing how is it, what type of form of the carbon dioxide system would dominate at certain pH. Well, at a very, very low value of pH, the carbonic acid is the stable one. And then this carbonated water would start to be fizzy or bubbling with carbon dioxide. And this is more or less what happens at some places in the world. I don't know how carbonated bottled water is made. I suppose it's lake water. Or from some spring or something like that, but it's hardly a difference between a spring or lake water. Probably it's also carbonated artificially, but perhaps in some cases it already contains considerable amount of carbonate ions or hydrogen carbonate probably, and if it comes to the surface, maybe this is also slightly dependent on pressure and such things. It comes to the surface, it should have some possibility to evolve carbon dioxide. But I think it's all mineral waters that you buy on bottle, that is cheating. It's not natural carbonated water, even though it may occur at some places in the world. But I'm not sure. I think it's cheating. But you can do it. You can take a carbonate rock, for example, that is soluble, a little bit soluble. And then you pour acid on it. And what will happen? It will start to bubble from carbon dioxide. And this diagram shows approximately that. So a lot of diagrams, strange discussions, but I mean the background of all of this is not very tricky. I mean, carbonate ions, they are stable in basic environments, but not in acid environments. So this is a reason why, for example, minerals like calcium carbonate, the only reason I'm using calcium carbonate is that it is directly a mineral containing a species in the carbonate system. If you would have some other minerals that are silicates, for example, they are much more common, but then they can in principle react with carbon dioxide. So you have a similar, from the atmosphere, so you have a similar situation, only that the silicate minerals, they are much more stable. They will, however, also vitrify, that is decomposed due to acid-base reactions with the solubility from the environment. And thus the solubility will depend on whether we take account of this vitrification or not. The simplest case is to check the solubility in water and not taking care of any hydrolysis reactions. No reactions anyway, anyhow. Or possibly hydrolysis with water. Why not? Water is not a strong acid and neither a strong base, but at least it has minor acid-base properties. Or in an even more realistic point of view, the solubility of these minerals, they depend also on the environment. And if the environment is pure air, that is nitrogen, oxygen, and argon gas mainly, then I suppose nothing happens, at least due to acid-base reactions. But there is also carbon dioxide in the atmosphere, quite a lot. This is not a strong acid, but it's a better, stronger acid than water is. So then one could perhaps try to estimate the solubility and how the solubility is increased. I tried here to enter some formulas. Can you see this writing? Is it too small maybe?
I suppose it's fine.
Yeah. The calcium carbonate is dissolved as usual, and we have an equilibrium constant for that. So what to do with the carbonate ions? Well, there is this reaction hydrogen carbonate and carbonate and hydrogen ions that is occurring now and then. And if we reverse that one, we will have this reaction in the hydrogen ions combined with carbonate ions producing hydrogen carbonate. And the equilibrium constant is not the Ka2 as it is from right to left, but rather the inverse of that. This, since we have reversed right and left side, we change them towards each other. For this common, we look upon the hydrogen carbonate usually as decomposing to carbonate and hydrogen ions. But why not write the equation backwards? Then we can just invert the equilibrium constant. So doing that, now let's see, can I try to add some annotation? Then taking equation 1 and equation 2, we can just skip those two. And here we have calcium carbonate going to plus H plus, goes to calcium ions and hydrogen carbonate. H plus, then it would be like pouring acid on it. But noting that water is auto-dissociated to a slight extent, at least, in hydrogen and hydroxide ions. So we could add that one. And then we would be left with this equation with and the equilibrium constant would be the product of the individual equilibrium constants, Ksp times Ka2 inverse times Kw. This is in principle possible as long as you don't construct a reaction that is hardly feasible. I mean, is it reasonable that you put calcium carbonate reacting with water, dissolving a little bit, and then the carbonate, in a way, due to the fact that it is dissolved in water, disintegrates into hydrogen carbonate and hydroxide ions. Well, it's not entirely fantasy. It could perhaps, at least at low levels of calcium carbonate, be the effect. So then we could actually try to use a similar type of setup. We know now the K for this reaction. And we know that we start with pure calcium carbonate and pure water. So what do we form? Well, for example, X number of calcium ions, how many, same number of hydrogen carbonate ions and same number of hydroxide ion. So expressing this equilibrium constant as the right-hand side divided by the left-hand side, and the left-hand side is still calcium carbonate, its unit, because if you have a piece of marble in a bottle of water, then after it has a little bit of it has dissolved, it is the thing that is left is still marble. And since you're not measuring the substance amount or concentration, you're measuring, you should have in this equilibrium constant discussions, you should have the activity, that is the how does this residue of calcium carbonate look like or behave compared to standard calcium carbonate? Well, it is exactly the same, but perhaps a little bit less, but less amount in kilograms or moles. But the activity is similar. And then we can also argue for the conserved unit of water. Some water is actually used up, but the rest of the water is still approximately pure water. It's still approximate, since this X will probably be quite small. It's hardly producing a very, very different solution. So the activity of water is still approximately unity. I say approximately unity, and the deviations from these values, they could be in the order of a few percent or something like that. And if you have a way to estimate that deviation, you could perhaps use that value instead. Or that it's probably an overestimate a few percent. Maybe it should be 0.999 or something like that. But let's not be that. Let's not try to be that accurate, because we are doing probably other approximations that is not visible here. But in principle, the K is the right-hand side product divided by left-hand side, so it's only X3, which means that X will be 8.96 times 10 to the minus 5. Is this different from what we had before? Let us remember 8.9 times 10 to the minus 5. What did we have before? Before we had 5.8 times 10 to the minus 5. This is without hydrolysis with water. This simplest of all calculations for the solubility of calcium carbonate does not take into account any other side reactions, but only taking into account the side reaction with water produces not a very much bigger results, but at least I mean 5 and nearly 9 here. It's not 50% more or something like that, maybe. Considerable amount. So, but there is a considerable more amount of work and thinking associated with actually deriving this, and there may be errors in this construction. So maybe we would find a more complicated formula, for example, less hydroxide ions. The quote between hydrogen carbonate and hydroxide is perhaps not 1:1, but some other ratio, and then we will have another formula. But for sure, we will arrive at a value here that is not similar to the previous value without any side reactions. So a more realistic, what time is it? 9:44. Should we have a break before we take this one?
Okay, sure.
I think so. We can take a break to now. Let's see.